and again, when you go with the architecture of any processor, I told you, Varun, right? We need to discuss about the register organization of that specific processors. Okay. So this is at the like what to say, like at initial level, but our syllabus has it's little bit advanced, Varun, right? We are just going to exploit the advanced computer architecture. So here the advanced computer architecture in the sense how well the hardware is exploiting the parallelism in the day-to-day microprocessors. So the syllabus is about this. You got it? So whatever the processor we are having today, how well it is good for parallelisms, like what kind of parallelisms can be done on what type of computer architectures. So we are going to explore these things in your rest of your syllabus. So when it occurs parallelisms, right? It may be a data level parallelisms or task level parallelisms. So are instruction level parallelisms. So based on this, your unit has been organized. So unit 1, we are going to see about the instruction level parallelisms, and unit 2, we are going to see about the data level parallelisms followed by thread level parallelisms, and unit 3 is we are going to focus with the request level parallelisms. So request level parallelisms nowadays, right? You know about this data warehousings. So wherein, right, I mean, multiple request is going to get comes, and I mean there is no dependent between those requests, but anyhow, right, all requests has to get serviced. So that is the kind of request level parallelisms, and how well the data warehouse computers is going to support those things. Okay, so that we are going to read in third unit, and finally the fourth unit just we are going to cover about the memory. I think this we you already read in CO. So the extension to that regarding this cache optimization, because when you go with the risk based architectures,
Excuse me,
like
ma'am. Are you sharing your screen, ma'am?
oh, no, not it no.
Okay.
Just an introduction only. I'm not sharing any screen, but I need to record it, right? Okay. The thing is, right, I'm not going to go with the PPT, but right, I will put a PPT. So because we have PPT in our hand since the last semesters we did, so we have a PPT for all the syllabus. I mean, for the entire 4 unit. If suppose if I try to share the PPT, probably, right, this course is going to be, I mean, class is going to be like a theater mode. So it just many times, right, I may read it, I may read the PPT, and you may or may not listen it. So instead, right, like I will, I mean, whatever there in the PPT, I will try to write it like my regular classes. I will try to do it, and later, right, you just go with the PPT also. If you have any doubt in that, you can ask me, because like whatever there in the PPT, I'm just going to cover. Or else, right, we will do one thing. I will finish it up, and then right at the end of the class, I will open up the PPT, and just I will try to just I mean, simplify what is there in that PPT. Okay. So now, right, sorry. Will that be a problem with Mozilla? Okay. Is it visible? The screen is visible.
Yes, ma'am.
Okay. So right, we will just go with the syllabus today. Today's objective, right? We will see the classes of computers. So what are the different class of computers that are available, and the different classes of parallelisms that can be done in applications. So with respect to applications, what are the parallelism available with respect to applications, and like what's the hardware that are available to support these parallelisms. Okay. So support for parallelisms. Okay, so these things just we are going to say this. So this is the objective of this today's class. And so when you just go with the basic things, so nowadays, right, the computer technology, it's a tremendous growth, right? So the growth rate has been progressive, and it's visible to us also. So there is an incredible progress rate, growth rate in computer technologies. The reason behind, can anyone say what might be the reason behind this? Okay, so they're saying there are two major reasons. One is the virtual elimination of assembly language programming. Other one is the operating systems. So we have a standard vendor independent operating systems. Okay, so these are the two major reasons that may leads to the growth rate in computer technologies. So these two you know very well, because see, whenever you are designing any hardware, okay, so if you have any hardware, it's a processor, okay, so if you have any processor, so hope you know, so which will be sit on top of the hardware normally, right? You will have your OS, okay, so on top of your OS, right, you will have your application programs. So normally, right, the hierarchy will be like this. Clear? So the thing is, right, the first thing, whenever any new hardware has been designed, so what is the first software that has to be developed? Can anyone say? Assume that if you're just going to design any hardware, so what might be the software for that hardware that is required? Please don't, are you, just you can, don't go in chat, you can speak it. Can anyone say for this hardware, so the software, because you know very well, right? So whatever you want to execute on that hardware, any hardware, right? So probably, right, it should be its machine code. Only then, right, it can able to execute, and which is capable to do that. Which is capable to do that. Compiler, right? So compiler, so that is very very important. Yeah, so right, whenever you just go for any hardware, the designing a compiler is difficult. That's what, right, yesterday I discussed, when you go for a risk based machines, the emphasis will be much on compiler side. Hope you remember, right? I told you, right? So for a risk, it is a software, and when you go with this risk, it is all about the hardware, because hardware will take all the responsibilities, but in case of risk, it will never do it. So only you have like one byte instructions, that instructions will be executed by a risk based architecture. So convert to a one byte instruction is all done by the compiler. Okay, so nowadays, right, again, these things is also eliminated, because you know about what is that Java, you read, right? Like you you read, yeah, you read, right? So why they say, right, Java is a platform independent? Why Java is platform independent? And some will claim is Java is not a platform independent also.
Like we can write code for using Linux operating system or Windows, and we can deploy it in any platform.
Okay. Yeah, that's the thing. The actual meaning is this, right? When you say it as platform independent, irrespective of the OS, right, we can able to execute the operating. You can able to execute the Java code. But actually, what happened behind is, do you think will it be feasible? Because how come a code that has been designed for an Intel will it be suitable for assume like what to say, some ARM based? How come a code for CISC will be able to run at risk? Actually, what is happening in Java case? So you are just giving your source file, right? You are going, it goes to the compiler. Clear? The output of that compiler is what?
Class file.
Yeah, you have a bytecode, isn't it? Okay. So the bytecode, where it is going? It is going to the Java virtual machines, and then and finally you will get the executable file, and it is get executed. Actually, this what happening in case of Java. The thing is, this alone is platform independent. Clear? Compiler is platform independent. We are not designing a compiler, because I told you here, whenever you are going to design a compiler, so probably it is for a platform, any hardware. But in case of Java, what they are doing is they are designing on compiler. That compiler is independent of any platform. The output of the compiler will be a bytecode. But when you just go with any hardware, you will have a Java virtual machine. Okay, here you will have a Java virtual machines. Every processor should have this. Okay, clear? Every processor should have this JVM or OS. So it may be a part of OS. So it should have its own JVM. So what it does is it will convert this bytecode to the corresponding, whatever the corresponding processor, for that it will execute. Okay, so what they are trying to say is designing a compiler will be much harder than the designing this JVM. What is this interpreter, right? So this may take, assume that roughly I'm just scaling up. Assume if it takes 30 days to design, so hardly it may take half days to design it, because with the bytecode it is easy for us to write the executable codes. Okay, so that's why they are just claiming Java as platform independent. Clear? So nowadays, these things all has been eliminated. So we don't have I mean, it doesn't have you don't have like an independent operating systems. Everything comes as like a kind of virtual machines. So with that we can able to execute anything. Even you might come across with the virtual box and all, right, on Windows. With the help of virtual box you can run the Ubuntu. Okay, so you have this Windows, you have the hardware. So on top of that, using VirtualBox, you can have this, I mean, something called virtualization support, right? So nowadays, whenever you are going to purchase anything, you have this virtualization support. So all has been run is independent of the platforms, independent of the processor. So we can do everything with respect to the softwares. So because this is the major reason for the growth rate in computer technologies. Okay, so majorly these two reasons, and they are just going for I mean, in the textbook they are given another four more significant growth rate of that, right? The first one is the high performance microprocessors. So nowadays, whatever the microprocessor we are having now, I mean, assume that the microprocessor that is at 2020, let it be, which is literally equivalent to the supercomputer at 2010, maybe, or I mean, less than that, 2005. You got it. So that much performance improvement is happening with the respect to the microprocessors. It is almost equal. So what is a supercomputer that is done in 20 years? Now what the desktop, whatever we are having in our hand, right, as a desktop or the laptop or the mobile. So that is performing all those things. Okay, so I mean that much capability the current day microprocessor is having. Next, the next impact is also the cost. So with respect to cost, sometimes it may be feasible to purchase, and that may lead to new classes of computers. Because date back to 2010 or 2005, so weren't only like supercomputers and desktops were in pictures, but after that, so laptop comes, and then the mobile devices, and then we have tablets, so and so. Okay, so because of this cost, we have arrived at the new classes of computers. And the third thing is semiconductor manufacturing. So even in digital, we are we have started, So initially, right, it started with the vacuum tubes and the transistors, and then right, we have million trillions of transistors, which leads to the microprocessor. So that also semiconductor manufacturing is also has a great impact with the growth rate of computer technologies. And the fourth one is the hardware innovations. These hardware innovations, so here they're saying us nowadays, right? You may have this word, you may know this word, uniprocessors. Okay, so when you talk as a uniprocessor, it is a single processor. Nowadays, right, almost it has been stopped. The research on uniprocessor has been stopped, and slowly, right, it has been moved to something called what? Multi-processor. You got it. So right now, because you know, right nowadays, right, when you just take any processor, so you may come across like Core i5, i3, i3 or i7s, right? So you may did like a dual core or a quad or 8 core. Okay, you got it or not? So nowadays, right, it has been. The trend is. The hardware innovations has moved towards multiprocessor rather than the uniprocessors. So almost the research for uniprocessor has get stopped. So compared to the multiprocessors. Okay. So these are the major reason for the growth rate of the microprocessors. Okay. The first one is the performance. So as I told you, right, nowadays whatever we are having, even what the mobile we have in our hand is much more powerful than maybe, right, it may be more powerful than our laptop also. Okay, so the next one is the cost effective and semiconductor manufacturing, and finally, right, the hardware innovations. Because now when I talk as a multiprocessor, this is the one which is provide a path forward. Since we have this one, right, when it is a uniprocessor, we have a single core. Okay, when it is a uniprocessor, you will have a single core. When you take as a multiprocessor, so probably, right, what is that? You have a multiple cores. Okay, so definitely you have a multiple core. When you have a multiple core, what it provides? It provide a path for what? Can anyone say?
Parallelism.
Yes.
Parallelism.
Yeah, of course, right? Yes, right. It's provide a path for parallelisms because we have four cores. What we need to do with four cores, right? So, to make use it efficiently, whatever we have, that has to get parallelized. Clear? Understood. Since there is a hardware innovations with respect to these multiprocessors, so it clearly provides a path for the parallelisms. So when you just go with the parallelisms, so again, so it's provide a path for the parallelisms. So this is very important. So when you talk as parallelisms, so the next question, in what way we can do we can do the parallelisms. So what are all the ways we can do it? So again, the question is, the answer to this is one is right, ILP. So we can go for instruction level parallelisms. I think you read this in your what is that? CO. How we are achieved instruction level parallelisms. The next one is data level parallelisms, or TLP is thread level parallelisms, and RLP is request level parallelisms. So we are just going to cover about these things in your syllabus. I don't know whether you heard these words in your CO, but hopefully you might have heard this word. Have you heard this? Instruction level parallelisms. Okay, at least let it be. Have you heard this word?
Yes,
Yes,
ma'am.
ma'am.
Good. What is that? At least, right? Okay, let it be. I will go for a few more. I will go for three-stage pipelining. This have you heard?
Yes, ma'am.
This also you heard. Then you don't know this. So actually, what is this? Oh, sorry. Okay, I mean, you just take this pipeline. I take a three-stage pipeline. Let it be you have a fetch, you have a decode, and here, right, we have an execute. So what happened? Assume that this is my ALP code. Let it be. I have this like add r not comma r1 comma r2 something sub okay r2 comma r3 comma r2. So something some instructions compare r1 comma. Okay. Something like this. Okay, assume that this is a like a toy example. Okay, don't take it seriously. So just to make you clear with this, I'm just going with that. So here, what is happening is, so when you just take a pipelining, so we have three-stage pipeline. So assume this is instruction one, this is instruction two, and this is instruction three, and this is the instruction four. So initially, right, instruction one at first clock cycle. Okay, this is first clock cycle. The first clock cycle, instruction one will be in the fetch stage. During the second clock cycle, instruction one will be in fetch, instruction two will be in decode stage. The third clock cycle, instruction three
Ma'am, instruction 1 is decode and instruction 2 is
sorry,
fetch.
sorry, yeah. This is instruction 2 and this is instruction 1. Okay, so instruction 2 will be in decode stage and instruction 3 will be in execute stage. So in a single clock cycle, what is happening? All the three instructions are executing in parallel. Can we say this as parallelisms? Instruction level parallelism or not? Because three processes happening simultaneously in a single clock cycle. I mean, when you just go with the first case, we can't do it because the first initially it has been loaded. Probably that this is going to be nothing. But during second clock cycle, instruction two will be fetched. At the same time, instruction one will be decoded. Yeah. At the third clock cycle, instruction three will be fetched. Instruction two will goes to the decode stage, and instruction three will goes to the execute stage. And again, it purely depends. After executing the instruction, sorry, this is one. Okay, after executing the instruction one, it may change, something may be changed also. At that time, what has to be done? So assume that let it be, we will go for this case. I mean here, right, I'm just assuming instruction one is compare. After comparing, after executing, the result may change also. You got it or not? So there is no need of executing. Let it be, we'll take like this. So compare r0 comma r1. So I'm doing add less than r0 r1 comma r2. Rs subtract greater than r0 comma r1 comma r2. Let it be like this. So when I'm comparing, if suppose if it is like let it be. So initially what will happen? So now right, this is going to be instruction one. Okay, so this is instruction one, this is instruction two, and this is instruction three. So according to this, at the third clock cycle, so what will happen? You have an instruction three here, instruction two here, and instruction one here. So what is instruction one? Instruction one is the compare instruction. So it is just comparing R0 and R1. I just put the value as 8 and 6. When it is comparing, what will happen? Will this instruction execute? Add less than instruction execute. Hey,
No, no, ma'am. No.
let these things are not. In CO,
Yes, ma'am. When they both are equal.
I am going to complain to Sangashiran sir because he called and said, this time we reduced your burden. I thought everything, I mean, all the problems you have programs we solved using Tail, like that and all, he said. Have you did or not? Not in chemistry answer class, sir. That's the answer. Have you did in Tail?
Yes, ma'am. Some basic programs we did.
Oh, okay. At least you did. So then you must know about these instructions. Don't know, yes or no? I mean, I don't want to waste time.
When we compare it, if R0 is less than R1, then this
By
addition.
compiling, we cannot get to know right. It is going to be less than or equal to, because we are going
Yes,
to
ma'am.
provide a data during runtime. Okay. So like keep remember, compiler will nowhere responsible for logical things. Only is right. It will generate only the object code. Anywhere, right? It will create only the object code. So it won't do anything. So actually, does it know anything? Since it has been there in the memory contiguously, it will be loaded here. But according to our case, since I1, after comparing, oh see, this one I am given, right? What all those things are?
Less than, greater than.
So those are all what?
Flags.
Condition.
Yeah, conditional
Execution.
execution.
Conditional statements.
Because you know, I mean, as somebody said, right? We have something called what? Flag registers. So you have some components like the sign flag, overflow flag, negative flag, or something zero flag. So many flags are there. So automatically, right, when you are executing this compare instruction, these flags will be affected. Okay, so accordingly it knows when it is less than what has to be there. So probably some negative flags has to get affected, and accordingly it will execute. We no need to worry. Okay, but here it just very clearly see, after executing this instruction, is I2 should be there, because which is the one next going to come. This is the one. Will I2 should come here?
No, ma'am.
Huh?
No.
It shouldn't, right? Because this should not execute. Because I3 has to get execute. Immediately what will happen? What happened? The pipeline will be flushed. Again, it has been reloaded, because after this, whatever was to get executed, so accordingly, right, it will perform. It will flush out, and again it has to get loaded. So probably there may be some cycle wastage over there. So that might be the problem with respect to this. So that's why, right, they will go for some predictions and all. I think the later you read branch prediction, right? Have you read or not?
Yes, ma'am.
You read branch prediction. So what's the advantage of that?
Saving clock cycle.
So you know, right? Because why do you need a branch prediction? For 10 mark question, huh?
Clock cycle will be wasted and to overcome that
This mainly, I mean, this example clearly is mapped with that. You understood? So just unnecessarily, right? We need to avoid flushings. Okay, so that's the reason, right? They gone for these branch predictions and all. Let it be. I don't. Okay, this. I mean, just for explaining this ILP, I just gone for this. Okay, so pipelining is the one way wherein, right, we can able to achieve instruction level parallelisms. Similarly, right, we have for DLP we have similar kind of architecture. For thread level parallelisms, we have some architecture. For request level parallelisms, we have some kind of architecture. So we will discuss in the forthcoming slides. So till this is clear. Okay, so I think that this part you have to be important for your syllabus aspects. Okay, so mainly, right, almost the research over uniprocessor has get stopped. So whatever the processor that are available in the market today, all has been into multiprocessor. Since we have a multiprocessor, so probably, right, it provides a path for the parallelisms. And when you talk as a parallelisms, it can be of any type. It can be instruction level parallelisms, data level parallelisms, task. This is instruction. This is data level, task level parallelisms, and request level parallelisms. Okay, so these things we are going to see how to achieve these parallelisms with the help of the computers that are available today. Okay, so this is an example of how pipelining works. This is what I need to say. So the first, right, we'll just go for the classes of computers. So it just when you just take as a class of computers, so broadly, right, they are categorizing into 5 different types. Okay, so one is the personal mobile device, desktop, server, cluster or warehouse scale computer, and embedded computers. Okay, so the computers just they classified into 5 different types. The first one, we will discuss this. So this is very, very important. So when you're going with the different classes of computers, so the critical system design issues. So it may vary depends upon the requirement. Okay. So we will discuss one by one design issues when you are discussing this. Okay. So this is very important. Clear. So you know the price of the system and the price of the microprocessor involved may varies. It depends upon the computers what they are using it. Okay, so the first one, right? We'll just go with the PMD. So PMD is what? As a personal mobile device. So what is this actually? So since it is a mobile device, so probably, right, it is a collection of wireless devices. So probably, right, you have a multimedia user interface. So the best examples it includes your mobile, tablets, etc. Okay. So when you take as a design issues with respect to PMD, one is, right, we will be very much care about the responsiveness. Okay. Because mostly, right, we need it should meet the real time performance. So when you talk as real time performance, see, if suppose if you're executing any task, probably, right, we have to for any task, if you take any task, we need to provide a maximum execution time. That is very important because if you take any real time, just when you talk about a real time systems, normally we can classify into 2 types. One is hard real time systems, another one is as soft real time systems. So what makes the difference between a hard real-time system and soft real-time systems? So in case of hard real-time systems, whatever the task we are running, it has to be executed within that deadline. Assume an aircraft, if something is happened, like within 5 minutes, there should be some alternate. I'm just roughly I'm saying. So some within 5 minutes, some has to get open up or something, some wall has to get to something. Got it? Okay. So such type of task will comes under for real-time systems. Okay. So which means, right, it has to meet out within that deadline. Or else, right, what will happen? Definitely there will be some catastrophe. It may lead to some catastrophe with respect to hard real-time. So moving on to soft real-time systems. I mean, right, here also, it doesn't mean that it should meet the deadline, but anyhow it will meet it. But what will happen is there may be some degradation in the performance. That's the difference. Okay, but it may be allowed to execute beyond the deadline also. It may not lead to any catastrophe. Because in this case, what will happen? Suppose if something is, assuming in an aircraft, if something is not working within 5 minutes, so maybe there is a place, I mean, there is a chance for the flight get break, right? So that kind of task will comes under the hard real-time systems. and there is other kind of task, software time systems. It may be executed. I mean, doesn't mean that it has to meet out the deadline, but it may get executed after that also. But there may be a degradation in the performance, but at the same time, right, it may not lead to some catastrophes. Okay, so with respect to the personal mobile devices, this responsiveness is the major important critical design issues. So other than that, right, the two more design issues are, one is the cost, always the factor, and the other two important thing is, one is the energy, another one is the storage. Because when you just talk as an energy, so these two are the battery and the power consumptions, and also the battery storage. So both, I mean, has to be taken care with respect to the PMD. And when you just go with the storage, again it is with respect to the memory. Some inbuilt memory will be there. So there, whenever you are going to design a application for the PMD, the emphasis will be much on the code rather than the data, because we don't know the data size. So we have to be very much aware while writing a code for personal mobile devices. Okay, it is not like our desktop or like a server. So while you are designing an applications, so you have to be much, very much, I mean, emphasize on the code. Which means with respect to the memory, you have to be, I mean, it has to get optimized. Okay, and the next, this side is like you have a battery and power, and I mean, the one thing I need to say, because I'm doing that BDD thing, like right, normally right, when you just charge, when you're doing it, charging, we are doing it, like every battery will have some life, isn't it? Yes or no? Yes or no?
Yes, ma'am.
Yes, right. Because every see, some they are saying some battery cycles. So it is there. What will happen is, wherever you have a battery, there's some battery cycles will be there, and they will say, right, like that battery cycle is, maybe it may be expired after that life cycle, and it depends upon our life. So it may be again, it may work after that battery cycle also. So here what I need to say is, sometimes what I do is, I will, you have a power bank, I will put it onto the power bank, and then I will use the power bank for the I mean, for my mobile. So ultimately what I'm doing is, I'm just wasting up the battery cycle of the power bank, and also parallelly I'm just wasting up the battery cycle of the mobile. So what we can do is, instead putting on, I mean, when you have a chance to put a power to the mobile directly, you can put it to the mobile directly rather than using the power banks. You understood or not? Because so every devices will have its own battery cycles. So unnecessarily, I mean, please don't waste it. If you have a chance to plug in directly, you just go with that. Okay. So okay, this is all about the personal mobile devices. Okay. So the next one is about desktop. So when you just go with the desktop, you know, I mean, I don't want to give much information about the desktop. So mainly, right, for graphical performance, the design issues. So for graphical performance, it has to be good, and the price is also a matter. Okay, this is for the desktop. The next type is a server. So when you just go with this server, right, it is just we can share, right, it is a shifting to a desktop computing, shifting the desktop computing. We are just almost, right, we are shifting the desktop computing, and we are given much importance for the file and the computing services. With respect to servers, so we are more majorly focusing with the file and the computing servers. So almost, right, nowadays, like large scale enterprises will have these servers. Okay. So again, right, when you just go with the issues, I mean, the critical factors to be considered for the server is, one is the availability, because clearly, right, when you talk as a server, so we may have a multiple request. So clearly, right, it has to get available. Just say for example, ATM or whatever the cases, So whatever we are doing it right, I mean you might have heard a word like this, right? Zero downtime. What is this? What is zero downtime? At least I've heard this word.
No, ma'am.
No. See, like we are not in position to purchase a server, or like the people who is providing the services to us, right? They will say it is a zero downtime, which means right, it is something like 365 days into 24/7. So in a single day, right, it will never get. So I mean, in a single minute, it won't get off. So that right, we are just saying it as a zero downtime. So that is nothing but the availability, right? So when you just go with the ATM, all those things. Sometimes we are getting server is not responding, but still, right, that is a very critical issues with respect to the servers. And the next one is the scalability. When you talk as a scalability, the scalability in terms of all right, it should be in computing, on the memory, or even IO bandwidth, because this is very important, right? When you have a request, IO request to that server, it must be in a position to handle this. So this is very, very important. Okay, so it should be scalable. So it depends upon the applications, it should be scalable. And finally, the throughput. So you know about the throughput. Say suppose if it is a banking oriented applications, how many transactions that happens per minute, or if it is a web page kind of things, how many web pages it has served per second. Okay, so those are all the metrics that have been associated with these servers for these kind of applications. Okay, so just when you just talk as a server, just we are shifting the desktop to the higher level, wherein it is morely focusing with the files and the computing services. And almost like all the large scale enterprises is using this, and the major factor is availability, scalability, and the throughputs. So the next one is so this are nowadays we have been very clear. Clusters are, you can say it as warehouse scale computers. So this they say like this, warehouse scale computer as WSC. So here what is happening is, I mean, you may have a doubt like what might be a difference between a server and a cluster. So it's clear. So when you're just making something as a cluster, the cluster can be connected by means of a desktop or by connecting a server through a LAN. LAN is a local area network, and it just give a visualization as if right we are having as a single computer. You understood? So this right, this is the view of the clusters. So or any warehouse scale computers. So it will be like this. You may have many desktops or you may have many servers. So like and it has been connected by means of a LAN and gives us a illusion as a single computers. Okay. So and again, right, when you just go with the performance aspects, so one is the price, price is the matter, and the performance, how well it is. I mean, the transactions, how well it is servicing is another question. And the major problem nowadays that they are facing with the cluster or warehouse computer is the power and the cooling. How to provide a power, and at the same time, right, the heat dissipations, how to provide the cooling systems. And even right, in some cases they are given 80% of the effort have been made on these two things. Whenever they are going for designing a cluster or a warehouse scale computers, so most of the effort will be onto this, both powers and the cooling systems. And many research have been almost towards this, and the availability. This should also be done. Yeah. And you may heard a word this supercomputer also. Have you heard this?
Yes, ma'am.
So when you take this as a supercomputer, I think we can say this also a kind of a warehouse scale computers. But here, what happen is these things, the cluster or warehouse scale computers, It may be useful, right, when you just go for applications like social networking or something like video sharing or games or whatever it is. Such cases, these things will be useful. But when you take supercomputers, so it is mainly used for scientific purpose. Okay. So this supercomputer will be used for the scientific purpose, wherein right, what they will do is they will give us some batch of programs, and the batch of program will run for a period of time. Will run for some period of time, even for a week. Not only time is don't think like 1 hour or 2 hours, even for a week it will execute and give the output. So mainly right, when you just talk as a supercomputer, it is wholly for scientific purpose. This is very important. Yeah. So this is the fourth type, and just moving on to the fifth type. So it is embedded computers. So yesterday we had discussed this, right? What is embedded?
Specific applications.
Yeah, right. It's just when you just go for specific applications. Say for example, like a microwave, printers, or even in cars they are using it, or else, some onboard unit, OBU. So they may serve the word as onboard unit. So those things, right? They are making use of some microcontrollers or switches. I mean router switches. So those cases they are making use of the embedded computers. And nowadays, I mean, once upon a time, when you talk as a PMD is what? Mobile devices is also a kind of embedded. But do you say is it embedded nowadays? No, right? Because it almost like whatever your desktop or laptop is doing, your PMDs is also capable to do it. Okay, so this is the things. And again, when you just go with the embedded, the price and the performance will be the major critical design. One thing what they're saying is most of the controllers are like off the shelf component. What is this off the shelf? What is off the shelf component? So which means it is readily available. Okay, so off the shelf is like something like it's readily available. So you need to get the microcontrollers and whatever the devices we need. So we have to place it up and we have to design it. Assume that, say for example, suppose if you want to measure up the, show the temperature in a classroom or in a room, something like this. What is that? So simply right, you have some microcontroller and then some LCD display and a sensor. That's it. Okay, some temperature sensor. So simply right, we need to interface and we have to. I mean, here right from it we have to get it and then we have to display it. So this is readily available. The thing is right, we have to get it and we have to design a sophisticated software for our applications, and accordingly right we have to proceed. So that's why right, the most of the cases embedded computers they say it as the off-the-shelf components. Okay. So right, so these are the 5 different types of computers, classes of computers. One is the PMD, desktop, server, clusters or warehouse scale computers, and finally the embedded computers. Okay, so after that I have given the critical system design issues. Clear? Still there's any doubt?
No, ma'am.
Shall I? Okay. Do you have any class now? Anybody have a class now? Yes or no?
No, ma'am. After this, we don't have class, ma'am. Only at 3:15 we have class.
Okay. Okay. So shall I do one thing? So I mean, I'm not going to take entire 1 hour. At least 2.5 hours I will take it. Tomorrow I'm on leave. So can I take? Is it okay for you? Just half an hour. Tomorrow I leave you free. Or else, right, again, I need to find out the class on Thursday or Friday. You give some alternative. Thursday, Friday, I think we don't have a class. If everybody is free on the day, you tell 1 hour, I will come and take that hour. Or else, should I continue? Just half an hour.
Continue, ma'am.
Continue, ma'am.
Yeah, or only half an hour, okay? Just introductory part. Okay? So now, right, this we are seeing the classes of computers. So next, right, we'll see about the classes of parallelisms and the what are all the parallel architecture that are available to shoot this parallelisms. Okay, so when it, as I told you already, which leads to this driving force of the computer design, right? So when you just have a multiprocessor, that's the thing that leads to all those things. Okay, so when you just go with the application aspects, normally, right, we have two kinds of parallelisms. Okay, this just kindly listen carefully because from this here onwards, like just based on this only your syllabus is going to be. So we have two kind of parallelisms. One is the through application we can achieve only these two things. One is data level parallelisms, and the second one is task level parallelisms. Okay, so as the name implies, when it is a data level, so many data items that can be operated in parallel. At the task level, instead of data, right, task, we have a multiple task that can be operated in parallel. Okay, so but when you are going to design an applications for a parallelisms, only these two things we can do it, not anything else. Okay, one is the data level parallelisms, or we can go for the task level parallelisms. So if you take this data level parallelisms, um, uh, so what is that? Many data items that can be operated in parallel. So let it be. We go for some kind of matrix additions. I just will take an example as a matrix additions. Wherein right we need to add this. So assume that a 3 by 3 cross matrix we need to add this. So we have a loop something. Wherein right we have some instructions like okay A5 plus B5 and we are adding it to the C5. Okay. So if you take this instruction. How about this instruction? This instruction is going to be a single instructions. Do you agree this? This is the single instructions. But what this instruction is going to do? So, I mean, right, it is going to do this, right? A of 0, B of 0. So, A of 1 plus B of 1. So, A of 2 plus B of 2. Okay, something like this, isn't it? Yeah. So, these are all what? Different data items. But here we have a single instructions, but we have many data items. So what we can do is, so based upon this, we can parallelize. We'll see how to parallelize. Just for an example, I'm saying what is this data level parallelisms. Okay, so here the many data items are going to operate in parallel. So A of 0 plus 0 will work in one processor. A of 1 plus B of 1 will be in other. A of 2, B of 2 will be in other. So this is the way they are trying to achieve the parallelisms. You got it? Okay, this is the data level parallelisms. And moving on to the task level parallelisms, either we can say it as a task level parallelisms or sometimes right thread level parallelisms. So this also you may read right Java multi-threading. Have you read?
Yes, ma'am.
Yeah. What is that? What is the program? What is process?
Multiple threads are
Okay, what is process?
Run it once.
You know? Yeah. What's the difference between these things?
Inside the program, we have process, and inside the process, we have threads.
So I wrote something. Where it belongs?
You gave clear, ma'am. That's why it went, ma'am. Try to do undo, ma'am.
Only to keep only. Sorry. Oh, here I gave below. Okay. So like two kind of parallelisms. Okay, one is the data level parallelisms. The other one is the task level parallelisms. So data level parallelisms, I just gave an example. You just keep remember like CFI I equal to AFI plus BFI. So it means we have multiple data items that can be operated in parallel. When you just go with the task, so it may be a thread level parallelisms. So this what? So in case of multi-threading, what you're doing is, before that, I think I asked this word. What is process? What is program? And what is thread? Right? What is that? What is program? What is program?
Set of instructions.
Set of instructions. What is process? What is process? When you're executing that program, then we are saying it as a process. That's not right. When you're just giving a control alt delete, so what you are getting is a process. Whatever the process that are running, so we can visualize all those things. When you are executing the program, that we are calling it as process, or we can say programming executions. So what is thread?
Process contains thread.
Yes,
Light process
it's a
contains
lightweight
thread.
process. You can say it a small individual unit of a process.
Process.
You got it or not? Okay. So through a process we can spawn multiple threads.
Threads.
Clear or not? So that's why right we are saying it as a small individual unit of,
Multiple.
we are saying it as a threads. So this thread, right? This is also capable to execute what? Some task. So when you're, this is what you did, right? When you're did a multi-threading at Java, you have spawned multiple child processes, and thereby, right, each child process is executing its own task. So can we say that is a task level parallelism?
Yes, ma'am.
Yes or yeah, yes. So you can say this is a task level parallelism because two things, multiple tasks. So like task essence, process 1, process 2, process 3. So it may like that. When it goes like a thread level parallelism, processes 1 may have thread 1, thread 2, thread 3. That's the difference. But ultimately, right, some task is running in parallel. Clear? So this is about two kinds of parallelisms. I think you haven't come across with OS because when you read OS, there you know like how to go for task level parallelisms, how to span different process, all those things. But currently you just learn it. When it is a task level, you think as different process. When it is a thread level, a process can be divided into multiple threads. Okay, only these two things can be achieved with the help of the applications. Whatever the program we are going to write, only these two things can be achievable. So to achieve these things, so what we are saying is, we need a computer hardware, isn't it? So I told you we have only two kinds of parallelisms that can be done with the applications. To do that parallelisms, so probably we need a computer hardware which exploits these two kinds of parallelisms. So what are they? Here the two kinds I meant is only the DLP, another one is the TLP. So to achieve this, we need some computer hardware, and they are classified into 4 computer hardware. So totally we have 4 computer hardware architecture that are exploiting these kind of parallelisms. So of that, the first one is ILP. So here ILP, right? So when you just go with the instruction level parallelisms, you know what is just now we have discussed. So one is the instruction level parallelisms. The next one is vector architectures and GPU. Okay, the next one is the vector architectures and the GPU. And the third one is task level parallelisms, and the fourth one is request level parallelisms. Okay, so now right, we should have which, I mean, this is the general thing. Listen carefully. They said it's a 4 hardware computer that have been there 50 years ago to exploit these two kind of parallelisms. Instead of these 4 kind of architecture, nowadays, right, we normally write Finn's classification based on parallelisms. This is the one we are using now. So they are classified into all the computers will be fall into any one of the category. One is SISD, next one is SIMD, MISD, and the fourth one is MIMD. So this is single instruction, single data. Okay. The next one is SIMD. So the same thing, single instruction, multiple data. Another one is multiple instruction, single data. And the last one is multiple instruction and multiple data. This word nowadays, whatever the computers we are having today, all the computers will fall onto any one of the categories. One is single instruction, single instruction, multiple data, MISD and MIMD. Okay. So now, right, let it be. Now you define, I told you, right, only these two kinds of parallelisms are available. We need to achieve this parallelism in any one of the computers. Okay, so these are the different classes of computers we have. So we need to achieve these parallelisms in these computers. So when you take SISD, okay, first we'll take an SISD. So this, as name implies, it is a single instruction, single data. Have you come across this in your CO?
Sir said, but we forgot, ma'am.
Which sir? Okay, so single instruction, single data, clearly for uniprocessor architecture. So uniprocessor architecture, just now we have discussed, how will you achieve parallelism in uniprocessor architecture?
Multi-core.
Right.
Pipelining.
Yeah. Now what is pipelining? You understood or not? So SISD, it's a uniprocessor, and when you want to achieve parallelism in uniprocessor, it can be done with the help of pipelining. So probably in pipelining, what we are doing it? What we are doing it? It's an instruction level parallelism. This is what we did, right? We have fetch, decode, execute. When instruction 1, I mean third clock cycle, when instruction 1, 3 is here, instruction 2 will be here, instruction 1. So parallelly, right, what we are doing it? We are executing the instruction. Am I right or wrong?
Yes, ma'am.
Clear? So SISD is capable to instruction level parallelisms, and if you want to still because what we know is only two kind of parallelism that can be done with our core. One is the data level parallelisms, the another one is the task level parallelisms. With the ILP, which can be achieved, either DLP or TLP? Can we go for task level parallelisms?
DLP, data level parallelism.
Can we go for TLP? Is it possible? It is not at all possible because in a single program, it is a uniprocessor. It is going to execute a single process and it is going to execute parallelly the multiple instructions. Maybe those instructions may be on same data. You got it or not? So with the SISD instructions, with the SISD computers, you can exploit only the data level parallelisms. So keep remember. The next one, SIMD. The best example is GPU, or we can say it as vector architecture. Okay, so either it is a GPU. What is GPU?
Graphical processing unit.
Graphical processing unit.
So without knowing, we are just right. If suppose we have only NVIDIA kind of processor in our lab, we will try to buy it. Am I right? So we are doing it because what is happening nowadays is assume that you have like Intel Core processor, all those things, like i5, i7, all those things is there. It comes with NVIDIA processor also. This NVIDIA have more processing capability than the core processors. So what they started doing is they are trying to use this NVIDIA processor for the computing aspects. So some through some parallel programming language. So I think you have something like for NVIDIA, you have something like a CUDA. Some common unified defined architecture, something like it. It's a language, or we have like OpenMP. So one more is also forget it. Okay, these are the parallel programming languages. So this is for different architecture, for distributed architecture. But CUDA is a programming language which has been exclusively for using the graphical processor for our normal computation. They started using the graphical processor for our normal computation. So this comes under completely SIMD architecture. That is single instructions, multiple data. So I gave an example, right? The same example will take it up. So A of C of I equal to A of I plus B of I. Assume that we have like we need to add like 1000 plus 1000. Okay. So what they will do? You have the same instructions, but it has to get executed for this many times. So this many times it has to get added. So we have those many processors also. So what they will do is, they will put it onto multiple cores, and they will get the results. And they will get back. So there is a code to run this also. Okay. So the second architecture is SIMD. So the best example is the GPU or vector architecture. Now, what kind of parallelism we can exploit here?
Thread level parallelism.
Using SIMD, which parallelisms we can exploit?
Thread level.
Yes?
Data level.
Yeah. Again, data level. What we are trying to do, we are just instruction is same. Only thing is it is going to operate on different data. First processor is going to operate on this. Second processor is going to operate on A of 1 plus B of 1. You understood or not? Okay. Yeah. So SIMD is also exploiting the data level parallelisms. And the third case, MISD. Moving on to MISD. So nothing is like this. Multiple instructions on single data. So there is no class of computers till now they invented. So the last one is MIMD. So as the name implies, it is a multiple instruction and multiple data. As the name implies, right, we have multiple instructions and we have multiple data. So what parallelism we can exploit here? In MIMD architecture, we can go for data level or task level or thread level, whatever it is. Or else, one more is what? RLP. What is RLP? So it is a request level parallelisms. See the difference between this and this. When you just go with the thread level or the request level parallelisms, the difference is here, right? We have decoupled things because Because just now I told, when you just take a process that has been onto multiple threads, okay, but when you just go with the request level parallelisms, we have multiple users. Each users will give their own request. You understood or not? So right here, right, it is going to be decoupled. But in case of thread level, so it is not the case. Okay, so that's the difference between this RLP and the TLP. When you take an MIMD architecture, so we can execute any kind of parallelisms, but if we take a DLP with a little overhead, definitely with respect to overhead, we have to do it. So that's why, right? So for executing these things, they will use MIMD architecture. Mostly for these three cases, thread task, the request level parallelisms, they will go for MIMD architecture, and a DLP will be useful in SISD and SIMD architecture. If you want to do a data level parallelisms, we can choose SISD or SIMD. And when you want to do this thread level parallelisms, you can go for MIMD. Clear? I think with that I will finish it up on next. Tomorrow's class we will move on to next topic. So just I will conclude the sessions. Right? Initially, we just started with the introductions, how the growth rate, I mean, nowadays is very incredible with respect to in computer technologies. The major two reasons was only the virtual elimination of ALP, because nowadays nobody is writing a code on ALP, but still the core things, as I said yesterday, device drivers, those things comes under ALP only, and independent OS, that is the major important things. Other than that, these four major reasons, and our syllabus is focused more towards this 4-point hardware innovations. So wherein right, the concentration have been moved on to the multi-core processor. Since it has been on to multi-core processor, so parallelisms comes into a picture. So when you talk about parallelisms, we have multiple kinds of parallelisms. So with the help of which kind of architecture we need to exploit these parallelisms. Also before that, right, we have various classes of computers, PMD desktop servers, cluster or warehouse scale computers, and the embedded devices, and each have its own critical system design shifts, and that has to get met out. And parallelisms, only with the help of the applications we can do it. So either we can go for data level parallelisms or we can go for task level parallelisms. To achieve this, we have 4 hardware architectures, but commonly, right, this side, the left hand side, I given us like ILP vector architecture, TLP, RLP, but nowadays they are classified, unified, and they are classified into 4 general cases. One is SISD, SIMD, MISD, and MIMD. So when you want to do a data level parallelisms, first 2 is suitable, SISD and SIMD. Keep remember. MISD is not, no class of computers fall into that categories, and the last category is MIMD, wherein we can able to achieve instruction level, task level parallelisms. Okay, so with that I will finish up this session today. So if you have any doubt, you can ask me. And tomorrow's class, what should I do? Shall I shall I share the link of Venkateshwar?